So the other aspect of deciding whether or not a collision will successfully lead to a reaction is energy. When molecules collide, if you want to do a chemical reaction, they got to hit each other pretty hard. You are looking at breaking chemical bonds. When you're doing a reaction, you're going to make new chemical bonds, but you also have to break chemical bonds. And chemical bonds are really strong. Molecules wouldn't exist if their chemical bonds were not very strong. Molecules have a tendency to want to stay together. Even reactive molecules still exist. That is a stable orientation of all the electrons. And so the molecules need to really have a strong energy, a high energy to their collision. This is part of why the orientation matters. Not only do the right atoms need to touch, but you really kind of need that head-on collision where you're really going to see that sort of nice, strong energy that can break those existing chemical bonds and form some new ones. So when we're talking about the energy required for a chemical bond or chemical reaction, we can describe that using what's called an energy diagram. And the generic description of energy of a reaction is always this image, where we have kind of two plots. First, we're looking at progress of reaction. So this is kind of an abstract concept of what that means for progress of reaction. But this is the idea of basically how the reactant molecules change to become the product molecules. So over here, this would be like the start of the reaction. So you can see we have our reactants A and B. They undergo some change. Atoms rearrange partners, bonds are broken, different bonds are formed, and eventually we have what would be called the products. So in this case, they're listed as C and D. And we know that as you go along, A and B are stable molecules. So as you go to change them, you're going to lead to a higher energy state. So the energy goes up, and then you reach a peak, which is called the transition state, and then it goes down into the products. As the products are also stable molecules, so as you get similar to the products, you would get lower in energy. There is always a highest energy point. That highest energy point is called the transition state. The transition, you are transitioning from reactants into products. So that is where the change happens. So we can look at a real reaction and see what does the transition state kind of look like, or think about what that would be. So I have hydroxide, OH-, reacting with CH3Cl to make CH3OH plus Cl. And I have the structures are shown right there. And I can see that what happens is the oxygen is going to form, the red oxygen is going to form a bond with that black carbon atom. So it's going to form this bond right here. So for the reaction, those two things are going to need to touch each other because that's the bond you're trying to form. And you're going to break this carbon-chlorine bond. So the chlorine atom is that green sphere. It's going to be floating around by itself as a chloride. So it's going to leave the carbon. So the transition state is going to look something like this, where the carbon is still bonded onto all the hydrogens. And what is happening is you are forming the oxygen-carbon bond while breaking the carbon-chlorine bond. So you don't just like break a bond and have, say, broken apart molecules and then they form in. It kind of comes in at the same time. So you can see it's kind of this transition from this being a real bond into this being a real bond. So let's erase those. So these molecules, these atoms are moving, right? That's a part of these kinetics. There's a movement. This chlorine is moving away. That bond is breaking. And this oxygen is moving in. It's coming towards the carbon and forming that bond. So we will note this is a transition state. It's important to note this is not a stable molecule in any way, shape, or form. It has two not good bonds that are kind of elongated, not good sharing of electrons. This is not at all a stable molecule, but it just does, this is kind of the transition. You're moving from having the carbon-chlorine bond into having the carbon-oxygen bond. You'll note there's a double dagger out there. Those little two, that is not two plus signs. That's called a double dagger. That means transition state. So that is our symbol for transition state. So that molecule looking thing at the transition state is very unstable. And that is why it has a higher energy. And so the transition state is always this kind of like breaking bonds while forming bonds, but nothing is really happy. So it has a really high energy that's called the activation energy. The activation energy is the difference in energy between reactants and the transition state. This is oftentimes called the reaction barrier. And this is the minimum energy that you need to have for a collision to cause a reaction. So you can kind of think about this like, you're pushing something up a hill or a roller coaster going up a hill. If, say, you have this much energy, it just kind of stops and then rolls back down, right? You collide and the bonds, say, get stretched, but they don't break. You hit really hard, the bonds get long, and then you curve back down and you go back to the reactants, right? You got to really hit with enough force that the molecule can go over and then come back down, right? And so that sort of idea of how is there enough energy to make it over the peak and go over. So we call that the barrier. In general, most atoms, most collisions don't have enough energy to make it over the barrier, and that's why reactions don't just happen. So if you have a really high activation energy, you have really slow reactions. So anytime we talk about reactions that, quote, are really slow or say just don't happen, it's because the activation energy is really, really high. Sterics and orientational dependence of collisions can be restricting, but over enough time, it'll eventually happen. If you have a really high activation energy, over enough time, you will never have collisions that are strong enough. You will never have enough high energy collisions. High energy collisions are in general very rare. Really high energy collisions are exceptionally rare that, millennia would have to pass and they still wouldn't happen. When we look at these reaction diagrams, we can also show the overall reaction energy. So the activation energy, that barrier, that peak, is always there. That activation energy is true for an exothermic reaction, where, say, going from reactants to products is a decrease in energy. It's also still there for an endothermic reaction, where reactants to products is an increase in energy. The activation energy always is reactants to products, and it's always positive. It does not matter if it's an endothermic or exothermic reaction. Energy always has to go in to get over the barrier. Energy may be released afterwards, but you still have to get over the barrier. You still have to put energy in order to get over that barrier, to break those bonds, to get over and to get through into breaking that, into moving into the products. Everything is always activated. There are always barriers. Heat always is needed to get over. So overall, we can kind of look at our overall process. We have our activation energy, that transition state. This idea that you have that activation energy, we say that reactions are require an activation energy. You need to put energy in to activate them, to get them started. If there's not enough energy, if there's not enough energy to get over that hill, the reaction just won't happen. You need them to be activated. They are activated processes. Physical changes, melting, those are still activated processes. You need that energy to get in, to get it started, to get it moving. And that is distinct from the enthalpy change. But you can represent all of that on one graph. And I would expect you to be able to do this for any sort of graph. You should be able to draw this general idea that every single reaction diagram looks like this, always looks like this. There's always at least one peak. We'll see 2 peaks next week. Participation 2-3, question 2. Consider the following reaction energy diagram. A, what is present at point A? B, what is defined by the arrow labeled capital B? C, is this reaction exothermic or endothermic? This is the second question on participation 2-3, due Tuesday, February 3rd at 11:59 p.m. over on Blackboard. The link to the assignment is right below the document where there are the links to these videos. Following reaction energy diagram, this thing right here. What is present at point capital A? What is defined by the arrow labeled with capital B? And is this reaction exothermic or endothermic? So, with that in mind, collision theory tells us you need high energy reactions for a collision, for successful collisions. If you increase the temperature, molecules will move faster and they will have more high energy collisions. So every single reaction goes faster when you increase the temperature. Doesn't matter if it's a chemical reaction, a physical process, melting, freezing, whatever it is. At higher temperatures, everything goes faster because every reaction goes faster because your molecules are moving faster. Your molecules are moving faster, so they have higher energies. When they collide, it's more energy. The bonds are broken more easily. You can get over those activation barriers. And so increasing the temperature always leads to faster processes. That is one of the easiest ways to control a reaction. You want it to go fast, heat it up. You want it to go slower, cool it down. And so these ideas about collision theory, this idea about energies, can help us kind of figure out how these different kind of chemical behaviors that we've seen. We talked about the fact that propane, when you mix it with oxygen, doesn't react. This reaction has a huge barrier. There is a very, very high activation barrier. That's why you can put propane and oxygen in a box, and if you let it sit there, it's never going to react. You can let it sit there for thousands of years, millions of years. Nothing's going to happen. It's just going to sit there. That propane and that oxygen is not going to react. You need something to help it get over that barrier. And that is the purpose of your match. You put that match in, that gives you a lot of heat. You can move some molecules go over the barrier. This reaction is then very exothermic. So what happens is some molecules react, they release heat. That makes other molecules react. They release heat. You get more and more heat. Then you get a chain reaction. So basically the reaction starts to basically make itself continue or propagate itself because it keeps releasing heat to have other molecules react. But you need something to get it started. There's a huge barrier to this process. The activation barrier is really, really high, which is good. That's why you can also use it as a fuel. It's good that it doesn't just burn in air. That would be very dangerous. We wouldn't really use propane. These ideas about controlling temperature, using temperature to control reactions, that's why cold-blooded animals bask. So lizards, alligators, turtles, that's why you see them lying in the sun. They're cold-blooded, they need the sun to regulate their temperature, and so they lie in the sun to make sure their body is warm enough so that chemical reactions can happen. You need warm enough temperatures to drive chemical processes. If you get hypothermia, that's what's going on. Your body is not able to keep itself warm enough to drive for chemical reactions to be happening. Your reactions can't get over the barrier. A lot of times people have this idea that like your insides are frozen. You're not frozen on the inside in hypothermia. That's frostbite. So you still have like liquid water. The chemical reactions just can't happen because there's not enough energy. Things are flowing, things are moving. They're just your reactions slow down because it's colder. And that's not good. You need those chemical reactions to run so that way you can, keep living. This is also why refrigeration works. You lower the temperature, so at low temperatures inside of a fridge, all chemistry slows down. So in a fridge, there's two, in sort of food preservation, first you'd have reactions with the air. So that would be, for example, things like bread going stale or fruit rotting or ripening and then going too ripe. Those are reactions with the air where the oxygen is reacting with it. There'd also be chemistry in microorganisms, right? If you got like little fungi or little mold, those grow faster when it's warm. Their chemistry would happen faster. And so if you put them in the fridge, you can just slow down all of those processes because it's colder in the fridge. Chemistry of cleaning. A lot of times we use hot water to clean things. This is carpet steaming. You'll use like steam cleaning on things. Heat does not always make things dissolve more. There are some compounds that dissolve less when they're hot, but at high temperatures, things dissolve more rapidly. So dissolving is still an activated process. There is an activation barrier to dissolving. It's low for a lot of things, but for say some dirt things or for say the effectiveness of soap, it just takes time. And so if you use soap with warm water, you've just sped up that time, which means you don't need to say let it sit or let something soak. And so you can clean more efficiently because you're using hot water. Any dissolving that's going to happen just happens more rapidly. Also, if you're familiar with self-cleaning ovens, a self-cleaning oven just gets really hot. That's all it does. I don't recommend using the feature in the summer. What ends up happening is you get really, really hot, and then the oxygen inside your oven starts to react with the grease and the grime and the stuff you were trying to get out. And so that just drives those reactions. So you still have to wipe it out afterwards. A lot of times, if there's this idea that self-cleaning ovens just like clean themselves and you're done, it instead just makes it easy to wipe out. You can't wipe out, say, before it's burnt. You can't wipe out, say, this like grime and stuff. It just cooks it and it turns it into ash that you can then wipe out. It's the same reaction that oven cleaner does. And so it's the same idea. You're just using, say, oxygen from the air in the case of self-cleaning oven. That has a really high barrier. So you heat up your oven like 500 degrees Fahrenheit or higher, and you use that. With oven cleaner, it's the same exact chemical reaction, or same idea, same reaction from the perspective of the grease. You're just not using oxygen from the air. You're using an oxidizing agent in the cleaner that adds oxygen into the grease. But it's the same idea. It's the same reaction. It's the same ash you create that you can wipe out afterwards. But the main difference is just that it's more reactive, so it has a lower barrier. That the oven cleaner, that happens with a lower barrier, so the reaction happens at room temperature. Oxygen from the air, you need to get really hot before that barrier, before it can react with the grease to overcome that barrier. So self-cleaning ovens, their special feature is just that they're built to withstand high temperatures. If you have an oven and you crank it to the highest setting, you can like warp the oven. So I don't recommend doing that to clean your oven. It would work if you got your oven hot enough, but it would also potentially break the structural stability of your oven. So do not recommend.
Participation 2-3, question 3. For each of the following, determine if it will increase or decrease the rate of a reaction. A, decreasing the temperature. B, dissolving solid reactants into a liquid solution. C, breaking up solid reactants into smaller pieces. This is the third question on participation 2-3, due Tuesday, February 3rd at 11:59 p.m. Link to the assignment is right below the document where there are the links to these videos. Again, for each of the following, determine if it will increase or decrease the rate of a reaction. A, decreasing the temperature. B, dissolving solid reactants into a liquid solution. B, breaking up solid reactants into smaller pieces. Okay, there were 2 questions on participation 2-3 in this video. Can you believe it? 2 questions in one video. I think there's only one more video left. Yeah, one more video in this set. It's a middle part of chapter 12. Looking for any more questions on the participation assignment. I'll see you there.